Hello everyone. Today I would like to talk about the fundamental theorem of line integrals and review the basic concepts of line integrals. So, what do we have here? Right here we have the fundamental theorem of calculus for line integrals. In this case, here is our line integral. F, capital F, is a 3D vector field in 3D space. In this case, we are taking the gradient of the little f dot dr. So little f is actually a scalar function in 3 dimensions, in 4 dimensions actually. So it takes 3 variables, x, y, and z as parameters. Really important thing to note here. Because we already set f is equal to delta little f, because we already set f is equal to delta little f, the gradient of little f, what we're saying here is this theorem only applies if f is conservative. In chapter 16.2, when we computed the line integral, we needed to do the brute force method, and it took a long time. Now, if the field is conservative, we have a much easier time with this. We can directly use the fundamental theorem to give us the answer. Right here, what I did was we actually split this expression into the derivative and vector expressions. So now we just need to evaluate the function of r, so it's our path, at the endpoints t1 and t2. Then we plug them into our potential function, little f, and by evaluating the difference, that is our line integral. But this convenience comes at a cost. Just to rephrase, this only applies if f is the vector field f is conservative. So when you're doing a problem, always test whether the field is conservative. If it is conservative, use this method right here. If it's not conservative, unfortunately, you're going to have to do the brute force line integral. All right, we still have time. Good. Next, I want to draw the line integral and give us a quick recap of what it does. So, let me erase just some of this, and I want to draw a 3D coordinate axis. So here's our z, here's our x, and here is our y. Now, let's say I plot the field using red markers. You can just think of the field mathematically. But let's say we plot it using red. Now, this is our vector field f of x, y, and z. If it helps, think of the red field lines as a positive electrical field. An electrical field from a positive charge. You can think of it that way. Now, let's trace our line through blue. Let me just connect the dots. Right here. So here's our path. Next, I'm going to draw our position vector r of t. So recall that from Math 1C. Whenever we have a vector function, it's going to point from the origin and into whatever value it is. So right in here is pointing along this curve. So here's our R of t. As time progresses, it's going to start here. Let's call this t1. And let's call this t2. It's going to start here. So at time equals to 1, it starts here. And as time goes on, it's going to point along this curve and move, all connected to the origin. And when we reach time 2, it's going to end right here. But in this case, when we actually compute the line integral, we have to take the derivative of it. So let's say your vector function r of t points here. When you take the derivative of the vector function, it is always tangent to r of t. And in this case, it will be tangent to the curve. Now, this is our basic setup right here. Let's talk about the importance of parameterizing. So we know that in this case, we plug the x, y, and z of the values of the vector function r of t into the vector field function f, or gradient of little f here. Why? Well, in the case of a line integral, you note that you have vector fields going all over the space here. But a lot of those field vectors don't touch your specific curve. By doing this, what we are basically doing is we're saying, all right, we're going to only consider these vectors, the ones that actually touch this curve. The rest of the vectors we ignore. So let me just draw it up here. This is what we're doing. We're only considering the field vectors that are positioned on our curve. The rest of the vectors, they're there, but we ignore them. Now, we have our r prime of little t. As we've just discussed, our r prime of t is basically our tangent vector to the curve. So instead of the r of t, our original vector function, pointing to t1 and slowly transitioning to t2, our r prime of t, our derivative of the vector function, will now start at t1, and then it will slowly move along the curve and back to t2. So what's going to happen right here? At this point, r prime of t is right here. And at this point, it's going to be right here. What we're going to do is we're going to say, all right, here's our r prime of t, and here's our field vector. We're going to take the dot product of that thing. As you recall, the dot product of two vectors is defined as, let me use a different color marker. So, here's our f, and here's our, let's say our vector d. F dot d is defined as the product of their magnitudes, or their vector lengths, times the cosine of the angle between them. So, we're basically finding how much these two vectors, we're finding out the dot product of these two vectors here. So as this moves along the curve, whenever it touches a field vector, we're going to compute the dot product. Then when it moves here, we're going to compute this different dot product. And you will notice here that the angle between them is changing. It's changing over time along this path. Here, the angle is large. It's larger than 90 degrees. But here, it's smaller than 90 degrees. And another thing to consider is, once we've computed this, once we take the dot product of one area, because we're taking the integral, we're summing up all the dot products here. R prime of t is moving. And as r prime of t is moving, we're using the integral expression to sum up the total values of the dot product from t1 all the way to t2. Now, I hope this helps clear up the basic intuition behind the line integral. This concept applies for all line integrals in all fields, not just for conservative fields, but for non-conservative ones as well. Next, let's talk about what's going on here. So, we know that our delta function, a gradient of our function little f, is a function of x, y, and z. But in this case, by doing r prime of t, we're parametrizing it along this curve. And so, what we're doing is, we're actually changing this to, we're actually changing into its derivatives. And so, this is no longer a function of just x, y, and z. Instead, it's going to be a function of x of t, y of t, and z of t. Because we're parametrizing it along this curve, we're only focusing on the x, y, and z values in this three-dimensional space that fall onto this blue curve. Now, just to recap, for the dot product, this is one scalar value. When we take the line integral here, we're summing up all these little scalar values, whether they be positive, in this case, where the angle between them is less than 90, negative, where the angle is greater than 90, or 0, if they're perfectly 90 degrees apart. And we would get a scalar value for our line integral. But why do we end up with a function over here? Well, the explanation has to do with parametrization. So, let me erase all of this. Recall that we just did this. We took the dot product of these two together. This is the vector fields, the red markers. So these are the red vector field lines that fell onto the curve. And we're taking the dot product of them over the function. So instead of this returning a scalar value, it actually returns a scalar function. Because this is a function of x, y, and z, now parameterized in t, and this is also a vector function described parameterized by t, then what it's going to look like is x of t, y of t, and z of t. X of t, y of t, and z of t basically describe the blue curve that I just described. So this produces a scalar function. This scalar function also has values of x of t, y of t, and z of t. So it still returns these three variables, but because we parameterize them according to t, they're on the blue line. So we're not considering all possible x, y, and z over space. We're just focusing on the ones that fell onto the blue line originally. So, if this gives us a scalar function, that means when we do this here, when you take the integral of a scalar function, you're going to get a scalar function. Let me just call this whole expression a function of t. I will remove the x, y, and z just to drive the point home. So, if you integrate this, you will get a new function, g of t. This is our antiderivative right here. This just goes back to Math 1b. So we're just integrating with respect to one variable. Now, in this case, when we do this, let's say this, when we take the dot product, let's say we end up with a new function, little g of x of t, y of t, and z of t dt. When you take the integral of that, you're simply evaluating the antiderivative of those points. But notice here that the x, y, and z, they're still all parameterized by t, because when we parameterize our function, we basically lose information and focus it only on that one line. So to show it a little mathematically, the book has a similar example on this. I just tweaked the variables. So let's say we have instead of saying r of t, I'm still going to say r of t, but I'm going to do a variable change halfway. So this is what we have here, just like our expression right here. Next, when you take the dot product of these things, of these two vectors, you can reduce the expression into the partial derivatives times the derivative with respect to t. This is just a chain rule. And so, actually, there's a better way. So let's say this is our vector here. We will call this partial of f, and we'll call this partial with respect to x. But here, remember that we parameterized our x on that curve. So x can't be anywhere. We're only focusing on that curve. That means we're taking the partial of f. And here our f is of x of t, y of t, and z of t. We're taking it with respect to x, but our x is parameterized by t. Next, we do the same thing for y of t and for z of t. And then when we do r prime of t, we basically have the derivatives of x, y, and z parameterized by whatever function of t there is. So now it would be this. Now, when we take the dot product, what this is going to turn to is this. So, this is what we have here. We just have one sum. Plus these two components multiply each other, then we plus the next two products. Okay, so here's our giant integral. Now, this looks awfully like the product rule. I'm sorry, the chain rule. The chain rule for multivariable expressions. So, let's see if we can pull the derivative out. So by using this, by using the multivariable product rule, by multivariable chain rule, we pull the derivative of t out. So notice here, we're integrating the derivative of this function f, but we're also integrating with respect to t. So when you evaluate the integral, you basically just end up with the original integrand in the center. So this is what you have. This is your final answer. Now, in the case of the line integral, we have 2 points, t1 and t2. So if let's say we have t1 over here, this just goes back to Math 1b. We basically change this into the fundamental theorem of calculus for regular integrals. You put this as t1, y of t1, and z of t1. And this becomes x of t2, y of t2, and z of t2. I hope this explanation makes sense. Don't worry if you don't get it the first time. This is a pretty tricky concept. It's a very beautiful concept. All right, good luck, guys.